So, the Langmuir Isotherm. So we start by talking about the mechanism of adsorption. And I'm just going to do that very briefly. And I'm going to do it for a gas phase molecule A coming into contact with a random surface. So I'm going to use this, nomenclature M, but I'm going to say M is a surface molecule. Okay. And there's adsorption given by Ka. And there's desorption given by Kd. And this becomes a new interaction pair. So we could think of this as an encounter pair, Am on the surface. Okay? So, and this could be for physisorption or chemisorption. And the rate and the value of the equilibrium constant, so in other words, we remember the equilibrium constant for this will be the forward reaction divided by the reverse reaction, so Ka over Kd. The value of that rate constant is also a good indicator if something's been chemisorbed or physisorbed. So if the equilibrium constant is much, much greater than 1, that typically means chemisorption. So if K is much, much greater than 1, typically that's chemisorption. Doesn't have to be the case, but that's very typical. And if K is much, much less than 1, that's typically physisorption, assuming I can spell this word. Okay. So what I want to show here, I wanted to kind of get into this mechanism, but because we're kind of nearing the end of the semester and I'm running out of steam, I just want to show that using, that if we talk about here this theta that I think I forgot to mention over here before, theta, this is our number of what we call monolayers or molecular layers. So it's the number of adsorption sites occupied versus the number of absorption sites available. So when theta equals 1, we have a true monolayer. We have a complete monolayer. If theta is less than 1, we have like patches of add atoms. And if theta is greater than 1, we have what we often call a multi-layer. Now, typically, multi-layers are only observed in things like water or things like ammonia. So water, this is what I did in grad school, is I looked at water monolayers and multi-layers on atmospheric surfaces. Water will definitely just keep adding and adding and adding. It will add multi-layers. And that's because of the hydrogen bonding network that it can create with itself. Other add atoms won't necessarily create multi-layers. And that's interesting from a surface chemistry point of view, just from the perspective of if you have some surface, but it's got a multi-layer of add atoms surrounding it, what is that surface even, doing chemically, right? So perhaps it's a big chunk of salt covered in water. Does it even look like a chunk of salt anymore, or does it just look like a particle of water? Hopefully you see what I mean, if that makes good sense, right? If I've got a salt crystal, but it's surrounded by multi-layer of water and other gas molecules come in to interact with it, they're really only interacting with water, not the salt that lies under the add layer, okay? So moving along, so we can talk about the production of monolayers, d theta dt, by the following, okay? So in terms of desorption, I think it's a little bit easier to work that out. That's going to be negative Kd times n times theta, where n is the actual number of surface sites available in molecules per square centimeter, because this is a surface, right? It's not a volume. And so n times theta gives us the weighted availability of surface sites, okay? whereas d theta dt can be given in terms of adsorption as Ka times Pa times N times 1 minus theta. I'm not going to hold you responsible for deriving these. Pa is the partial pressure of A, the add molecule. Okay, and N and theta still mean the same thing. And as it turns out, we can show using the steady state approximation that theta, the number of layers on the surface, the number of monolayers, is equal to K, this equilibrium constant, times the partial pressure of A divided by 1 plus K times Pa. So this is the very famous Langmuir isotherm, named for the scientist Langmuir. And as it turns out, there's a very famous journal, a very famous ACS journal called Langmuir. That's the name of the journal. It's very prestigious. And there's a lot of really cool stuff in that journal on molecular catalysts, ranging from environmental chemistry to material science. So maybe next year, if you're looking for something cool and hot topic, check out the journal Langmuir. There's some really, really cool chemistry in that journal. So what's important about the Langmuir isotherm is it gives you a predictive way to, under a certain set of conditions, like if you know the partial pressure of A and you know this equilibrium constant, then you know how many monolayers will be present on the surface. And for chemists like myself, for environmental chemists, we use stuff like this in large global climate models as a means of saying, well, if I have a salt particle floating around in the air, or if I have an organic particle floating around the air, so a surface, right? What do I expect its surface coverage to be in terms of water, or this molecule, or that molecule, okay?